My name is Daphne. Okay, my name is Daphne, and maybe you recognize it from the slides template that you've seen already earlier. I'm also from University of Antwerp, just like my supervisor John Kaudas, who gave this keynote talk earlier. And today I'm going to present to you the work that was titled Learning a Fair Distance Function for Situation Testing. So to start and give you a bit of context about what this work is about. So it's not that much about fair learning, where we try to make an algorithm that tries to predict fair outcomes. Instead, it's more like, okay, if we have a data set, how do we know how much discrimination there actually is in this data set? How can we detect discrimination? And in this work, for this purpose, we use the approach of individual fairness, where we basically determine for one dataset instance at a time whether they got discriminated or not. So this is a bit of a different approach to fairness than these group measures of fairness that have been talked about earlier. But one way to achieve this individual fairness, or at least study it, is situation testing. It's a methodology that is based on the principle of treating likes alike. So to explain a bit more, situation testing actually comes from the life sciences. So say we just want to see whether a company might be discriminating towards females. What we could do is we send two of the same resumes that are really identical in regards to work experience, in regards to education and everything, to a company. But if they only accept or invite to an interview the male candidates, we can of course say pretty surely, okay, so some kind of discrimination occurred because the female candidate was actually the same, except for the fact that she was female. So it's actually possible to translate this methodology of situation testing also in an algorithm. This was first proposed by Luong and his colleagues. But there, because often if you have a big data set with lots of different attributes, it might not always be possible to find equal instances to a one that you may be currently looking at. So instead, they propose to just look at similar instances. So say we have a data set like this, where we just have information about the sex of people, whether they got hired or not, and then their education level and their work experience. What Luong basically suggests to do is we look at the nearest male neighbors and nearest female neighbors of the candidates, and then compare the positive decision ratio among both groups. And here we would see that this positive decision ratio is much higher across the male neighbors. Hence, we can pretty surely say that there's occurs some kind of discrimination. So I think the idea of situation testing is very nice and also intuitive. But one big problem is, okay, but how are we actually going to select these closest, these most similar neighbors? And the distance function that was proposed in the original work, it is actually pretty simple, where they just take the distance between two features as the sum of the value differences between all features of both instances. And of course, this distance function is only defined over the non-sensitive attributes. So something like gender or race would not be taken into account in this distance function. As I told you, this distance function is a bit simplistic, and I'm going to show you why. So firstly, let's say we have a situation like this. Again, we have a data set about people who want to apply for a job. If we use the original distance function, we would here see that instance 1 and 2 are equally close to each other as instance 1 and 3, even though actually 1 and 3 are the same on a very relevant attribute, like the degree, where instance 1 and 2 are only the same on a pretty irrelevant attribute, whether someone is married or not. So in fact, it would be more desirable if we would just ignore this attribute in the definition of a distance function and would likewise ignore all irrelevant attributes. Another point is explained here. So say again a similar data set, but this time we are already ignoring the irrelevant attributes, but we added another attribute to the data set. The question we might ask here is, okay, is instance 1 and 2 more similar to each other, or instance 1 and 3 more similar to each other, as both instances only either differ on the degree or the years of experience. What we argue we should do here in this situation is actually look at the decision attributes and see here, okay, there seems to be a higher correlation between the years of experience and whether someone got hired or not. Thus, the years of experience seems to be a more important attribute in this sense and should therefore also contribute more to the distance function, concluding that actually instance 1 and 2 would be more similar in this example. One last requirement is we already learned about this indirect discrimination and these so-called redlining attributes, where sometimes attribute like zip codes may be correlated to a decision attribute because there's some correlation between a sensitive attribute and the decision attribute. In this case, of course, we also want to ignore a redlining attribute since it's only correlated to the decision attribute through the sensitive attribute. So here again, we listed all the requirements of a distance function. I think, or I hope it should be clear. And there has already been some work done on learning or defining a distance function that it's a bit more sophisticated than the one used by the original paper. One is given by ZHANG and his colleagues, where they show how a distance function can be learned from a causal network. What they basically do is they only define distances on attributes that are causally linked to the decision attributes, and there are also the causal effect sizes considered. Another approach is given by Inventor. It's a human-based approach where humans have to answer to queries, basically saying how big the distances between two features are. And based on the results of these queries, a distance metric is learned. So the disadvantage of these both approaches is that they kind of both rely on external resources, namely either the causal Bayesian network or human inputs. And those external resources are neither always available nor always reliable. Hence, learning a distance function directly from the data seemed to us like more of a better way to go for this problem. So learning a distance function is actually not a very new topic. It has been used before to improve the performance of clustering and classifying algorithms. And one distance function that you might use here, since of course, for instance, a regular Euclidean distance function wouldn't suffice, is you could use the weighted Euclidean distance function, where you basically multiply each value difference between features by some weight, which shows how relevant the weight is for a problem. And so we wanted to make an objective function that can learn the weights of this Euclidean distance, such that these requirements that I listed earlier for distance function are fulfilled. So for this, we set up the following objective function. Let's go through it step by step. So basically, firstly, what we do is, okay, we're saying we're minimizing this whole function here. And what we want basically is the distances between instances with the same decision label. We want that distance to be small, while distances between instances with different decision labels should be big. So hence we're subtracting these terms from this term. And basically what that should do to the learned weights is to make sure that features that typically contribute a lot to having a positive class label, that they should also get a high weight. Then we also added a regularization term, which basically makes sure that high weights are punished, especially weights that are not relevant to the decision label. And lastly, what we did is among these instances with the same class label or with different class labels, we splitted the data set according to the protected or unprotected group. to basically make sure that this correlation between a redlining attribute and a decision attribute is not learned when the weights are being learned. Okay, after the distance function is learned, it could be applied in the original situation testing algorithm, but then the question is, okay, how are we going to test it? How do we know if an instance is marked as discriminated, that this is indeed the case? For this, we mostly worked with synthetic data, or actually also these experiments will be the only ones I describe in the presentation. In the paper, we did a bit more, but let's focus on this. So we started with a causal Bayesian network. Again, this time we want to predict the wage of people, and we have information about their working hours, their skills, and their sex. Next to that, we added differing amount of redlining attributes. And what you basically see here is there's no connection between sex and wage. So this initially is just an unbiased data set. Then this unbiased data set we can use as the ground truth later on. But the data that we're actually going to test our algorithms on is this data set where we simulate a biased decision maker who's turning the wage of some people, or actually some women only, that was supposed to be high into a low wage. And to make this situation a bit more realistic, we only did this for women with neither very high amount of working hours nor a high amount of skills, but who were just this kind of border cases on the edge of getting a high wage. So then the algorithms we tested in our experiments were the original situation testing using either one of the distance function, namely either the one by Luong, the quite simple one, let's say, the one by ZHANG, which is based on a causal Bayesian network, and our learned weighted Euclidean function. And the way we measured our performance is by looking at the ROC scores of the discrimination scores. To remind you, the discrimination score is only defined over women with a negative decision label, because only they can be discriminated in this data set. And their discrimination score is defined as the ratio of male neighbors of a woman who have a positive decision label. So what we see with different amount of redlining attributes, initially all distance functions perform more or less equally good. Actually, we cannot even see the line by ZHANG because it is in fact equally good as the weighted Euclidean distance function. But we see that the distance function by Luong is the only one decreasing in performance. And this is, of course, the case because it tries to match, when finding neighbors, it also tries to always find neighbors that are similar on these redlining attributes that are actually not very relevant for the decision problem, which causes the distance function basically to neglect the more important features like working hours or skills. And as I said, the weighted Euclidean distance function doesn't suffer from this problem, while it maintains the same accuracy as ZHANG's distance function without relying on a causal Bayesian network. We did one other test case like this, where we basically had a very simplified example of explainable discrimination. In real life, it's of course a bit more difficult than this, but here in this case, there was already some link between the sex and the wage of a person, but this link could be explained by the fact that women had a lower amount of working hours in this data set. And again, we used this data set to simulate the process of a biased decision maker who again changed some decision labels from women with a high wage to a low wage. And again, we see a similar pattern. The distance function by Luong is the only one decreasing in performance the more irrelevant attributes are added. It is interesting to see here as well that in general, the performance of all distance functions is a bit lower than before, which is of course the case because it's now harder if you have a female instance with a low amount of working hours, it might be hard to find male neighbors that are very similar, since working hours was correlated or differed among the sexes. So basically, to conclude this presentation, we showed some requirements for the distance function. We showed how this distance function can be learned from the data without relying on external resources. And we showed how this distance function can improve the performance of situation testing. But it should be noted, like what I already said before earlier, sometimes it's a bit, especially with a bigger data set, so with data sets that contain this kind of explainable discrimination, it may still be hard to apply situation testing because you might not always be able to find neighbors that are similar enough to an instance in question. So one very open research question is still here, when are neighbors too dissimilar to base discrimination scores on? So just as a take-home message, we first showed this principle of treating likes alike, which is a nice principle to study individual fairness, but of course we should define what we mean by likes. And yeah, if you have any questions, I'd be happy to discuss them with you.